Hello everyone, welcome to online session of Maxwell's equations. I am Dr. Sadanand Kumar N, Assistant Professor, Department of Physics, AJ Institute of Engineering and Technology. Today I am going to discuss about Maxwell's equations. The topics for the discussion are vectors, that means the basics of vectors, the review of Coulomb's law, del operator, operations such as divergence, gradient and curl, line integrals, surface integrals and volume integrals, some problems from the curl operation and divergence. As we know that the physical quantities are classified as scalars and vectors, and the scalars are the physical quantities, they having only the magnitude but no directions, whereas the vectors are the physical quantities, they have got both magnitude and directions. You can think of the example for vectors as velocity, displacement, angular momentum, etc. In all these physical entities, they have the definite directions as well as the magnitude. So when we think of a vectors, we should know how to represent a vector. In the slide I have shown the length AB with the arrow mark. So which means the length AB is equal to R, that is the magnitude of that particular vector, and arrow mark designates the direction of the vector. Suppose if F is the vector, then F equal to R into AR cap, where AR cap represents the direction of that particular vector and R is the magnitude. So in turn I can write the expression for direction of that vector AR cap is equal to vector F by R, that is magnitude of the vector. Next, unit vectors. We should know what is unit vector and basis vectors for the next discussions. So when we think of a unit vector, it's a vector which has got the unit magnitude and the specified directions, whereas the base vectors, they are same as that of the unit vectors but oriented strictly along the coordinates in the given coordinate system and pointing away from the origin. In rectangular coordinate system, we represent vectors as ax cap, ay cap and az cap along the x, y, z directions respectively, which is shown in the slide. We also represent these base vectors as I, j, k along x, y, z coordinates respectively in the Cartesian coordinate system. Next, we will see how to determining magnitude of a vector when two vectors joining when the two vectors are joining. So for this explanation, let me consider the two vectors, vector A and vector B. The coordinate of vector A is x1, y1, z1, and coordinate of the another vector B is x2, y2, z2, which means the two vectors are separated by some distance or separation, which is shown in the slide. Now the vector AB can be written as x2 minus x1 into ax cap plus y2 minus y1 ay cap plus z2 minus z1 az cap. So in turn one can evaluate the magnitude of the vector AB as magnitude of vector AB equal to square root of x2 minus x1 whole square plus open bracket y2 minus y1 whole square plus open bracket z2 minus z1 whole square. So please remember this expression. This will help to evaluate the magnitude of a vector where there are two vectors are joining or meeting at a point. So please remember this expression. Next concept is a scalar product or the dot product of the two vectors. Let us consider two vectors, vector A and vector B. So vector A and vector B, which makes an angle theta, that is shown in the slide. then the scalar or the dot product of the two vectors is defined as the product of the magnitudes of the two vectors and cosine of the angle between them. So equation for the dot product or scalar product of the two vectors, vector A and vector B, is vector A dot vector B is equal to magnitude of the vector A, magnitude of the vector B into cos theta. So this is the expression for the scalar product of the two vectors. Now when we take the dot product of two unit vectors, say I cap and I cap or themselves, so that I dot I, that means I cap dot I cap is equal to 1. Also J dot J is equal to 1, K dot K equal to 1, all of them having cap because they are the unit vectors I mentioned. Because why it is 1, I cross I is equal to J cross J is equal to K cross K is equal to I dot I, dot product of the two vectors, I dot I, J dot J, K dot K is equal to 1. Why? Because the angle between these two vectors is 0. Because if you substitute that theta in the expression, the cos 0 is 1. Also, if you take the dot product of the another pair of unit vectors, say I dot j is equal to 0, and same is resulting for the another pair of unit vectors, say j dot k and k dot I, all of them are resulting 0. Even the other pairs you can think of I dot k, j dot I, k dot I, all these unit vectors resulting to 0 because the angle between these vectors are 90 degrees. We consider these dot products for writing the expressions such as work done, so that is force into displacement. Similarly for the electric potential E is equal to V is nothing but E, electric field into the distance, that is E into dl. That is how the expression for the electric potential. The next one is the vector product or the cross product. The vector product of these two vectors, say vector A and vector B, as shown in the slide, the resultant vector of the, as shown in the slide, which is in the three-dimensional view, the resultant of the vector A and vector B is vector C. So magnitude of the vector C is the product of the magnitudes of the vector A and vector B and sine of the angle between them. So mathematically you can write vector A cross vector B is equal to magnitude of the vector A, magnitude of the vector B into sine theta into A n cap. That A n cap represents the directions of the resultant vector, that is direction of the vector C. So you can see in this slide the vector C is equal to A cross vector A cross vector B, that is equal to, in matrix form, Ax cap, Ay cap and Az cap. Those are the unit vectors, or what you say, the directional vectors, and Axy, Ax, Ay, Az are the vector A component, and Bx, By, Bz are the vector B components. By the definition of vectors, we can write the cross product of the any two unit vectors. Say for example I cross I, that is equal to j cross j, that is equal to k cross k. All of them are resulting 0. Why? Because angle between them is 0. The sine 0 is 0 in the expression. Similarly, when you go for the cross product of the another pair of unit vectors, say I cross j, that is resulting k, I cross k resulting j, and j cross k resulting I. So in all these pair of unit vectors, the angle will be 90 degrees. Therefore the positive, the unit vector is resulting. Also k cross I, that is equal to minus j, k cross j is equal to minus I, j cross I is equal to minus k. In these three pair of unit vectors, the theta is 270 degrees in fact. That's why it is resulting minus that unit vectors. We can use this cross product for writing the expressions. For example, the force on a current carrying conductor kept in a magnetic field, the expression for the force is B cross I into L. Similarly, for an electromagnetic wave, the Poynting vector is vector P is equal to vector E into vector H, electric field into magnetic field. That's the meaning of E cross H. And also you need to remember the vector identities. The A dot B cross C is equal to B dot C cross A minus C dot A cross B. That's one of the vector identity that we have studied in your maybe 10+2. So using these vector identities, we can write the del, the symbol what I have shown in the slide, that is a del cross A. That means when we say del cross and physical parameter, it will be a curl. Therefore, the curl of curl A is equal to, again, del dot A. When there is a del dot function, that represents the divergence. Therefore, the divergence of A. Also, minus del square A, that is a gradient of A. Since it is del square, so gradient square A. So I repeat the vector identity, that is curl of curl A is equal to the divergence of divergence A minus gradient square A. Next topic is Coulomb's law. We have studied these Coulomb's law in PUC classes maybe, but let us recall the concepts which we have studied. And Coulomb's law, especially the applicable for the 2 point charges which are at rest. When the 2 point charges, say Q1 and Q2, are placed at a distance r, which is shown in the figure, you can see the slide, the magnitude of the electrostatic force between the 2 point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. So this is the Coulomb's law of electrostatics. So equation for the Coulomb's law, the force on charge Q2 due to Q1 separated by distance r is vector F12, that is equal to 1 by 4 pi epsilon into Q1 into Q2 by r square into r cap n, where r cap represents the direction and n represents the unit of the force, that is Newton, where epsilon is the permittivity of the medium. And what is the vector form of the Coulomb's law? So to represent the vector form of a Coulomb's law, consider 2 charges, say Q1 and Q2, which is at a distance r1 and r2 from the origin, that is in the coordinate system, that is shown in the slide as well. The separation between the 2 charges, that is Q1 to Q2, that is vector r12. So separation between 2 charges Q1 to Q2, that is vector r12, and the a cap 12 is the unit vector that represents the direction of the resultant vector. Now in this case, the expression for the Coulomb's law is already I have shown in the slide, that is F is equal to 1 by 4 pi epsilon Q1 Q2 by R12 square into R12 cap. Now this R12 cap can be written as the vector R12 divided by magnitude of the R12. That means the vector R divided by magnitude of the vector R. That will give the direction, unit vector, right? Next concept is electric field intensity or electric field strength. So electric field strength or the electric field intensity, that is defined as electrostatic force experienced by a unit positive charge. Expression for electric field intensity or the electric field strength, that is E is equal to F by Q, where F is the force experienced and Q is the charge, that unit positive charge. That's as per the definition of the electric field strength. E is equal to F by Q. Therefore, the electric field strength at Q2 due to the another charge Q1 is given by vector E is equal to 1 by 4 pi epsilon Q1 Q2 divided by R square into R cap into 1 by Q2. That is by the definition. Therefore, that is equal to Q1 divided by 4 pi epsilon into R square. That is the expression for electric intensity. Unit of electric intensity is Newton per Coulomb. Electric field, it is a vector entity, and the direction of the electric field is same as that of direction of the force. So, electric field can also be represented as the gradient of potential along the direction of decreasing potential. So, electric field can also be represented as gradient of potential along the direction of decreasing potential. So, equation in terms of equation, you can write this statement as electric vector E is equal to minus del V. Minus, where negative represents decreasing of potential, decreasing of potentials. Electric flux density or electric displacement D. It is defined as the number of lines of force crossing per unit area normally. So, electric flux density vector D is equal to flux per unit area. Suppose if phi is the flux, A is the area, then expression for electric flux density D is equal to phi by A. In case the flux lines are inclined by an angle theta to the normal, then the vector D can be written as flux divided by open bracket area into cos theta. This electric displacement D can also be expressed in terms of the electric field, that is vector D is equal to epsilon into E, and this expression will help to solve some problems. Please remember this expression, vector D is equal to epsilon E into vector E. This is the expression for electric displacement D. Electric displacement D is equal to epsilon into vector E. Next topic is the del operator. Del operator, it is a mathematical operator which is used to carry out a specific vector calculus operations. If the problem related to the Cartesian coordinates, then the equation for del is dou by dou x of ax cap plus dou by dou y of ay cap plus dou by dou z of az cap, where ax cap, ay cap and az cap are the base vectors. This del operation simply reduces the elaboration of writing the long standard steps when we deal with the vector operations such as gradient, divergence and curl. This operation del, in fact this operator del have the properties of vectors. Next topic is the divergence. Let us see what is the divergence and what way it will help to solve the problems, and we will see one or two problems also from the divergence topic. We had seen the dot product vector A dot vector B, also the cross product vector A cross vector B. Now we came to know that the operator del has the properties of vector. So we can now even consider the divergence of vector A and curl of vector A. That means del dot vector A, that is the divergence of vector A, and del cross vector A, that is the curl of vector A. Please remember, del dot vector A is the divergence of vector A. Del cross vector A is the curl of vector A. What is curl, what is divergence, I will explain now. This kind of operations means the curl or the divergence operations can be carried out only in the regions of space which has the presence of vector at every point in it. So divergence is one of the operations that can be done using a del operator. Divergence represents the magnitude of the physical quantity emerging or converging at a point. Divergence represents the magnitude of physical quantity emerging or converging at a point. You can think of example for divergence, tip of the fountain head. So here you can think of the diverging of water from the tip of the fountain head. So how the water will be diverging, and other example for the divergence, you may say that the electric field, wherein electric field lines are divergent in nature. So I have given two examples for divergence. You can just think what is divergence with this example. The tip of the fountain head, wherein the water will be diverging from the tip of the fountain head, and even in the electric field where the electric field lines are divergent in nature. Mathematically, divergence is obtained by differentiating components of a vector function. If f is the vector function, component of this vector function f are fx, fy and fz with respect to the position coordinates x, y, z respectively. So that divergence of the vector f can be written as dou by dou x of fx, dou by dou y of fy plus dou by dou z of fz, where fx, fy, fz are the component of that force field or the force entity. Suppose if the vector function is volume charge density, that is represented as again d, enclosed by a closed system, then the divergence of the volume charge density is expressed as divergence of vector d is equal to dou by dou x of dx plus dou by dou y of dy plus dou by dou z of dz. So remember, divergence can be evaluated in terms of the partial derivatives of the respective components, like dou by dou x of dx, dou by dou y of dy plus dou by dou z of dz. So dx, dy, dz are the components of that volume charge density along x, y, z respectively. So please remember these expressions, it will help to solve the problems. So it is important that you need to remember the right hand side of the expression, which is a scalar entity, which means divergence of a vector field always yields as a scalar entity or a scalar function. So if there is no inward or the outward flow in the system, then the divergence of that vector is 0. In that system, the divergence of vector is 0. You can think of the magnetic fields which form a closed loops. Since it forms a closed loop, there is no divergence at all. Therefore, divergence is 0. Mathematically, I can write the divergence of B is equal to 0. Why? Because the magnetic fields that will form a closed loops. Therefore, no divergence. Therefore, divergence of vector B is 0. We can understand that how divergence, there is no diverging, that is not from particular point it is diverging or emerging. So it is a closed loop. That is why the divergence of that particular field is 0. So a vector field whose divergence is 0 called as a solenoidal field. A vector field whose divergence is 0 is called a solenoidal field. Electric field lines from the positive charge, it is always a source of divergence, which means the field lines are always emanating or the diverging from the positive charge. Therefore, it's an example for positive divergence, whereas electric field lines which are always converging from the negative charge, therefore it's an example for negative divergence. You can see the figures where the positive and negative charges. From the positive charges, the electric field lines are diverging from that particular charge, whereas in the negative charge the field lines are coming to that particular point. We say it is converging. So we have seen the positive divergence and negative divergence. The direction of the field lines at any given point is the direction along which a positive charge would experience the force. So when this charge is placed in the field, so this clearly indicates the direction of the point charge, the charge when it is kept in a field. So that will gives the information about the direction of that particular charge when it experiences a force in the field. Next concept is the physical significance of the divergence. Actually, the physical significance is the divergence of the vector field at a given point is a measure of how much the field diverges or emanates from that particular point. I hope I have explained clearly the concept of divergence. Again, the physical significance of divergence is same. So how much the field of lines or the field that will diverge or the emanates from that particular point, that is the measure we are going to do with the divergence concept. So if there is a densely packed positive charges at a particular point, we can think of the large number of field lines are diverging. In other words, divergence is more. Next topic is the gradient. Gradient is the another mathematical operation that can be done using del operator. Gradient operation that will be performed to study the spatial variation of the scalar variable. So this operation is done to study the spatial variation of a scalar variable. Spatial variable in sense space variations of the scalar variable. So gradient operation on a scalar function yields a vector function. Quite interesting. The gradient operation on a scalar function which yields a vector function. So you can think of the variation of temperature in a room is an example for the gradient or gradient operation. It is represented as del T. It is shown in the slide. Del T, that is equal to dou by dou x of T into unit vector Ax cap plus dou by dou y of T into Ay cap plus dou by dou z of T into Az cap. So dou by dou x of T into Ax cap, that means the x component and the unit vector. Similarly, y component and unit vector, z component and unit vectors, that will give rise to a vector function. That's what I said, it's quite interesting. So gradient of a scalar will yield the vector. So these unit vectors will gives the information about the direction of that particular components. Right hand side of the expression is a vector. The direction of the temperature, or in this particular example, is the direction of maximum increase of the scalar variable or direction of maximum decrease of the scalar variable. So the first and foremost question arised is, if it is a vector, what is the direction of that particular vector on the right side? So the answer is it's quite acceptable. Direction of maximum increase of the scalar variable or direction of maximum decrease of the scalar variable depending upon the variations. Even electric field can be expressed as a gradient of scalar potential. So already I have defined it. So expression for the electric field is equal to minus del V, or in three-dimensional view it can be written as minus open bracket dou by dou x of Vx into Ax cap plus dou by dou y of Vy into Ay cap plus dou by dou z of Vz into Az cap. Here the direction is direction of the decreasing potential, that we need to note, because the negative sign that represents the decrease of the potential. And we will solve one or two problems from the divergence. The first problem is, find the divergence of the vector field. Vector A is given by vector A is equal to 6x square Ax cap plus 3xy square Ay cap plus xyz cube Az cap at a point P bracket 1, 3, 6. Here in this problem you are supposed to determine the divergence of the vector field A. The vector A is given, you write the given vector as 6x square Ax cap plus 3xy square Ay cap plus xyz cube Az cap. Now the general form of the vector A is Ax cap plus Ay into Ay cap plus Az cap. So Ax caps Ay caps Az are the xyz components, and Ax cap, Ay cap and Z cap are the unit vectors of the components. Now divergence of the vector field is given as del dot vector A is equal to dou by dou x of Ax plus dou by dou y of Ay plus dou by dou z of Az. Now you can compare the equation number 1 and 2. Already I have called the given expression number as 1 and general form as equation number 2. Now comparing these two, you can write Ax, that x component, as 6x square, Ay, that is y component, as 3xy square, and z component Az is xyz cube. You have written, just substitute these components, that is Axy, Ax, Ay and Az component in the divergence expression, so that you will get dou by dou x of Ax, that is 6x square. So a derivative of that is 12x. Similarly, dou by dou y of 3xy square, it's with respect to y, that is 6xy. Dou by dou z of xyz cube, that is 3xyz square. That will be the derivative. Now divergence of vector A is equal to 12x plus 6xy plus 3xyz square. So this is the expression for divergence. Already they have given at a particular point. That means the coordinates are given. X equal to 1, y equal to 3, z is equal to 6. It's given in the problem. So just substitute these x, y, z values in the divergence equation. So divergence of a vector field is 354. That is the answer for the problem. And the second problem, determine the constant C such that vector A, open bracket, vector A equal to, open bracket, x plus Ay, close bracket, Ax cap, that means the x component and the unit vector, plus open bracket y plus Bz, close bracket, Ay cap, y component and the unit vector, plus open bracket x plus Cz, close bracket, Az cap is a solenoidal. This is the problem. So vector A is given, you need to solve the constant C in the problem, and one more condition is given, the vector A is a solenoidal. whatever the vector they have given. So first you write the given vector, whatever the given vector that you have to write for equation number 1. And the second thing is the general form of the vector A, that is x component and the unit vector that you are supposed to write, call it as equation number 1. And compare the equation number 1 and 2, you will get ax, ay, az. Then expression for divergence of vector A. In the problem itself, it is clearly mentioned that the vector A is a solenoidal. In order to consider the vector A is a solenoidal, then the divergence of that solenoid is 0. Already I have explained under the theory concept, because it will form a closed loop. The magnetic field lines follow the closed loop. There is no divergence at all. Therefore, the divergence of that solenoid is 0. Therefore, for a vector, it is to be a solenoidal, then divergence of vector A is equal to 0. Then divergence of vector A is equal to dou by dou x of Ax plus dou by dou y of Ay plus dou by dou z of Az. Now you take the derivatives of Ax, Ay, Az substituted in the expression. So in the first term with respect to x, where in that there are two terms, the first one is x, that's with respect to x, you will get one constant there, it is 1. The second term there is no x term, therefore it is 0. Plus dou by dou y of y plus bz, again it is with respect to y, you have to take the derivative. So first term will get constant, that is 1 with respect to y, no, plus bz, there is no y term, therefore it is 0, plus dou by dou z of x plus cz. Here the first term is x, with respect to z we are taking the derivative, therefore it is 0, plus the second term it is with respect to z, it is c. Therefore the 1 plus c, that will be the value of the divergence of vector A. But we considered that for a solenoidal, the divergence of that particular vector is equal to 0. Therefore 0 is equal to 1 plus c. So c equal to minus 2. That is the constant we have solved. So answer for this problem, or c, is minus 2. Next concept is the curl operation. So curl operation is another important operations. It will give the information about the degree of rotation of a vector per unit area, or turning effect of the vector per unit area. So which means it will give information about the curling of a vector or rotating of a vector at a particular point. So curl operation on a vector function always yields a vector function. So now just you can think of the how to represent a curl. So del cross vector A, that will represent the curl of vector A. Divergence, the curl dot vector A. Gradient, that is del that vector function vector A. That is how it is. One dot means it is divergence. Simply there is no dot, no multiplication, it is gradient. If there is a cross mark, that means multiplication sign, then that will be the curl operation. So I hope you understood. Suppose if vector A is the function, it is its turning effect of a vector. If vector A is the function, the turning effect of that vector A at any point can be evaluated using the curl operations. That's what I mentioned. It will give the information about the curling of a vector or rotating of a vector or turning effect of a vector. Now it can be solved, actually it can be evaluated by using a expression. The curl of vector A is equal to, it's a matrix form, unit vectors Ax, Ay, Az cap, then derivatives, the dou by dou x, dou by dou y, dou by dou z, and the components, x component, y component, z component, that is Ax, Ay, Az. So in the matrix form you have to write the given vector as. So it is possible to solve and will get the curling of a vector or rotating effect of the vector. So using this methodology, one can simplify the above matrix and solve the problems. In other words, turning effect or the degree of rotation of a vector A at any point can be evaluated. One of the example for curl operation is magnetic field around the straight conductor carrying a current, and this can be expressed as current density J is equal to curl H. That means curl H is equal to vector J. So it's the another thing is you can express the curl of a irrotational vector as 0. That means curl of vector E is equal to 0, means there is no the curling or the rotating vector in such cases of the electric field. Therefore, curl of an irrotational vector, it is not rotating, therefore there is no rotation. Once the rotation is nil or 0, we can write the curl of that particular vector is 0. Curling of a vector field at a point P is a measure of the total field curls around that particular point P. That is shown in this slide. So in the figure A, figure B, figure C. Okay. So in this figure, whatever the field which we have considered, it is a magnetic field H. So curling of a vector in a magnetic field, that's what we need to understand in this figure. We can see the figure ABC in this slide. You can see the figure ABC in this slide. So it will gives information such that in a figure A, that means in the first circle, in fact, magnetic field vector curls around P, which is similar to electric field lines curling around the conductor. Yeah, electric field lines curls around the conductor when the current is passed through the straight conductor. So I hope you understood. So it is similar to the electric field lines curling around the conductor when the current is passed through it. So in similar situation, in the first figure, we can see the arrow marks that indicates the tangent to the curling of a vector. And in the figure B, you observe that the magnetic field vectors have a large magnitude all around the particular point P. So at the particular point at the center P is there. So in all around here the magnitude or the intensity is too high. Okay, magnitude of the curling vector is too high or large. Therefore, the more or vigorous circulation of the magnetic field occurs. So that is observed with the directions what we have shown of the curling of vectors. And if the one more case, we can see that the figure C, the field vector though have a large magnitude, do not have any turning motion at all. Hence, in this case, the curl H is turns out to be 0, which means there is no curl. Curl H is equal to 0 for an irrotational vector. So this is straight line. There is no chance of curling because the magnitude of the curling is too high. So magnitude is again it's very, very high. So there is no chance of rotating or turning motions at all. So in such cases, curl H is equal to 0. So in other words, the curl H is 0 applicable for an irrotational vector. Let us see the two problems of the curl operation. The first problem, there is a vector field defined by an equation. Vector F is equal to open bracket x square y ax cap plus 2z ay cap plus xyz az cap. Find the curl of vector function f. So here the vector function f is given. F is equal to open bracket x square y close bracket ax cap plus 2z ay cap plus xyz az cap. Call this is equation number 1. Now equation for force in the component form, that is vector f is equal to fx into ax cap plus fy ay cap plus fz into az cap. Call this is equation number 2. Now compare the equation number 1 and 2. Compare equation 1 and 2. From this you can write the fx component, fy component and fz component. So it is x square y as fx and 2x, 2z as fy and fz is equal to xyz. Now you can think of the definition of the curl there I mentioned the general form of the curl operation, that is curl of f is equal to first row is unit vectors and second row is partial derivatives or derivative of the components, that is dou by dou x, dou by dou y, dou by dou z, and is fx, fy, fz. Last row is the component of the particular vector. Already we have segregated it, and just substitute that components in the curl expression. Curl of f is equal to ax, ay, az, and dou by dou x, dou by dou y, dou by dou z. It is as it is in the expression. And last row, where we have substituted the components, that's fx, fy, fz. Now you have to solve this expression. So in this matrix form, first you have to take the first row and first column you leave, remaining that I have put the cross marks, leave first row and first column, and dou by dou y into x, y, z, and dou by dou z 2z. Therefore the curl f is equal to ax cap into ax cap, because since we considered the ax cap there, you have to leave the that row and that particular column. I put the line there and cross marks, dou by dou y of x, y, z minus dou by dou z of 2z, bracket close. Second term is always negative, minus ay cap, open bracket, dou by dou y. You can go for the second matrix form, which is same as that of the first one. Just for your understanding, I have given the second matrix. So here I put the central line, that means it is not supposed, you are not supposed to consider the second column and the first row, where you are considering ay unit vector, again open bracket, and cross multiply the other two columns terms. So I put the cross marks there, you can see there, and multiply, and dou by dou z, dou by dou x of x, y, z minus dou by dou z of x square y. It's a cross marks, okay. Close bracket, plus third one is again plus term, a z cap, again open bracket. You can go for the third matrix. There I have put the first row and the last column. It is put line. You are not supposed to consider, because that unit vector is considered outside the bracket. So a z cap, open bracket. Now you multiply dou by dou x of 2z and dou by dou y of x square y. Please remember, it is a cross multiplications in this operation. So now you have to take the derivative of this components with respect to the variables. So curl f is equal to ax cap, and with respect to y, the first term, there is the x, y, z is there, therefore xz minus dou by dou x of 2z. With respect to z, it is 2. Therefore the first term is solved, that is ax cap, open bracket, xz minus 2, minus ay cap, again open bracket, with respect to x term is there in that x, y, z is there, so yz is retains, minus dou by dou z of x square y. There is no z term, therefore term is 0, plus az cap, open bracket, dou by dou x of 2z. With respect to x, it is no term, 0, minus dou by dou y of x square y term is there, therefore x square retains, minus x square. So curl f is equal to, now xz minus 2 into ax cap minus yz into ay cap minus x square into xz cap. This is how you can solve the curling of a vector f. This is the solution for the curl f. This is the rotating effect of the vector f. Second problem, calculate the curl of vector A. It's given as, open bracket, 1 plus yz square, close bracket, ax cap, plus xy square, ay cap, plus x square y, az cap. In the second problem also, you have to write the expression for curl of vector A, that is equal to, in the matrix form, unit vectors in the first row, the second row the partial derivatives, and the third row it is the components. x component, y component, z component of the vector A. So it's very clear from the expression. If you write the general form of the vector A, it is ax into ax cap plus ay into ay cap plus az into az cap. So on comparing this, you will get ax as 1 plus yz square, that is written as ax, and xy square as ay, and x square y as az. So three components we got. You have written the matrix form. Now you can solve this vector A. Vector A is equal to ax cap open bracket. Similar way, you have to leave the first row and first column and cross multiply the second and third columns remaining terms. So if you cross multiply, that is dou by dou y of x square y minus dou by dou z of xy square. Second term, it is minus. Second term is always minus sign, ay cap open bracket. Now you leave the first row and the second column and multiply the first column and third column of the remaining terms. So that means dou by dou x of x square y minus dou by dou z of 1 plus y z square plus az cap open bracket. There you leave first row and third column, multiply the other two columns, the remaining terms, cross multiplication, that is dou by dou x of x y square minus, it's always minus, dou by dou y of 1 plus yz square. Now you have to take the derivative of it. So ax cap open bracket dou by dou y of x square y, with respect to y it is, therefore it is x square. Second term is with respect to z, there is no z term, therefore it is 0. Minus again ay cap open bracket dou by dou x of x square y, with respect to x it is, therefore 2xy it is, minus dou by dou z of 1 plus yz square, with respect to z it is, therefore first term is 0, 2yz, okay, plus az cap open bracket dou by dou x of xy square, with respect to x it is, so y square is remaining, minus dou by dou y of 1 plus yz square. So with respect to y, first term is 0, it's a constant. The second term with respect to y means y term is there, therefore it is z square. So y square minus z square, it is written. Now you rearrange such that the curl of vector A is equal to x square into ax cap minus 2 is taken outside the bracket, xy minus yz into ay cap plus y square minus z square az cap. So this is the solution for the curling of vector A. Next concept is the line integrals. So line integral, surface integral and volume integrals, that is especially used to evaluate the single integral or double integral, third integral. That means maybe problem is related to the one dimensional one, then you can go for the single integral, nothing but line integrals. If the problem is related to the surface areas or two dimensional one, then you can think of the surface integrals or the double integral. And if the problem is related to the volumes or three dimensional one, then you can go for the volume integrals. So remember, in case of closed path, there is a closed path and there is some situation there is a open paths. If there is a closed path, the integral with one circle within the integral will be there, whether it is line integral, surface integral or volume integral. Integral sign with some circle that indicates the closed path, closed surface or closed volume, like that it is. Okay, suppose if the single integral is there, which means it is a open path, okay, open surface, like that, that is the meaning. Okay, I hope it's very clear. Now let me start about the line integrals. To understand the concept of line integrals, let me consider a linear path of length L from P to Q in a vector field A, which is shown in the figure in the slide. That's in the first figure. Here the linear path of length L is imagined to be consist of large number of small elementary lengths. That means the long length is made up of small elementary lengths. The elementary length of dl, that means the length of each elementary divisions is dl. Now consider one such element whose length is dl at a particular point m, that is also shown in the figure, and draw a tangent to that particular point m. Now which makes an angle theta with the vector a. Then we can evaluate the number of field lines passing through the elemental length L. Since the elemental length dl, which is considered in the vector field, what is the vector lines or vector field is crossing that elemental length dl. Therefore, the number of field lines passing the elemental length can be written as vector A into dl. That's the first term. We want to know what is the total number of field lines passing the length L in a vector field. Length L, that means entire length of the material which we have considered in the vector field. Now, in order to evaluate the total number of field lines passing through the entire length L, we need to integrate the ADL, because ADL is the number of lines, field lines crossing the elemental length dl. If you want to integrate, if you want to know the total number of vector lines crossing the entire length L, we need to integrate the vector A into dl. So it will give rise to the total number of field lines crossing the entire length L. So this can be written as we say the total number of vector lines, okay, or vector field lines. So that is nothing but the flux through the length. Flux through the length. Flux through the elemental length is ADL. So what do you mean by flux? Flux is nothing but the number of lines of force passing per unit area. That is nothing but flux. Here the same thing is explained as the number of field lines or vector field lines passing that particular elemental length. Therefore, flux through the elemental length dl is A into dl. Similarly, flux through the entire length, that is phi, is equal to line integral ADL. You observe that if there is a single integral, there is no circle in the integral sign, which means it is a open path. So for a closed path, the total number of lines passing per unit length is nothing but the flux through the entire length in the closed path. Phi is equal to line integral ADL, but you can see there is a circle in the integration sign. Next concept is surface integrals. Surface integrals can be explained by considering the surface area S in the vector field vector A. So, this surface is assumed to be made up of the large number of elementary surfaces. So, whatever the surface, you can see the picture there, the big surface is considered, in which very small elemental surfaces are there. So, that together constitute to the total surface. So, that elementary surface in the total surface S is ds. Nothing but the area of the surface is ds. So now draw a unit normal AN to ds at a point M. That you can see in the picture. One small area is given, that is ds. So at that is that particular point is treated as M. So I have drawn the AN cap, that is the unit normal to that area, that means to the area ds in that particular point. Now in a vector field, imagine vector field elementary surface ds acts as a vector ds given as ds equal to ds into AN cap. So in vector surface area is a vector entity which acts as a vector, therefore vector ds is given as ds into AN cap. That's important point you need to remember in the discussion. Now the flux, as I mentioned, the number of field lines passing per unit area of a vector through the elementary surface ds is A into ds. That means the flux through the elementary area ds is A into ds. It means the number of the field lines or the vector field lines passing through the elementary surface ds is A into ds, vector into that ds. Now the flux of the field through the surface S is evaluated by integrating A ds, that means vector A into ds over the entire surface S. That is quite obvious because the total surface is nothing but the algebraic sum of the small surface areas of the total surface. Therefore, once if you get the flux through the elementary area ds, that is vector A into vector ds, you can integrate vector A into vector ds. It will give rise to the total flux through the total surface area. So phi is equal to surface integral A into ds. This represents the net outward flux of vector A from surface S. Then the total flux phi can be written as surface integral A into an cap close bracket ds, which means I have substituted vector ds as ds into an cap. As I mentioned, surface integral is also called as double integral. So if there is a circle in the double integral, indicates that a closed surface. If there is no circle in the integral sign, it's open surface. So next concept is volume integral. So in order to explain the volume integral, let us consider the volume in which charge distribution is taking place continuously and is referred as volume charge density. So that volume charge distribution, they consider an elemental volume dV. So in the whatever the volume which we have considered, in which the continuous distribution of the charge is taking place, in that we need to consider a elemental volume dV at a particular point m, which is shown in the slide. And the charge density at that particular point m, at the whatever the elemental volume which you have considered in the picture, okay, that will be rho v. Rho v, that is a scalar entity, that is a volume charge density in the elemental volume. Then the volume integral of the rho v over the entire volume v is volume integral rho v dv. So the volume integral of rho v, that means the volume charge density over the entire volume, is volume integral of rho v into dou v, where the integration of dv is nothing but integration of dx, dy, dz. So volume represents, so you have to integrate x, y, z dimensions. So volume integral is also called as triple integral. As I mentioned, if there is a closed surface, there is a circle in the integral sign into rho v dou v. So I will stop here. Thank you.